Welcome to the Explainer. Today, we're going to get into one of the most important parts of building AI, how to tell if the thing you built is actually any good, and, maybe more importantly, what to do when it isn't.
So let's just jump right in with a scenario. Picture this. You've spent weeks, maybe months, building an AI model to predict housing prices. You finally run it, and the results are just awful. The errors are huge. You're at a fork in the road, and what you decide to do next is absolutely crucial.
You've got a bunch of options, right? You could try to get more training data. Or maybe the problem is the opposite. You've got too many features, and it's confusing the model. You could try adding more complex features, or just fiddle with a setting called regularization. The thing is, any one of these could be the right move, but if you pick the wrong one, you could waste months going down a total dead end.
So this is the key. We need a smarter way to figure out what's wrong, a systematic way to diagnose the problem. And it all starts with how we organize our data before we even think about training our model.
This is the absolute golden rule of machine learning. You never, ever, ever test your model using the same data it learned from. Why? Well, it's like giving a student the final exam and also giving them all the answers to study beforehand. Sure, they'll ace the test, but it tells you nothing about whether they've actually learned anything.
The standard way we solve this is with something called a train/test split. It's super simple. You just take all your data and slice it into two piles. The bigger pile, the training set, is what you use to teach the model. The smaller pile, the test set, you lock away and don't touch. And that's what you use to see how your model does on data it has never, ever seen before.
And this one simple split immediately lets us spot two classic ways that models fail. On one side, you have overfitting. That's like the student who just memorized the answers. The model looks brilliant on the training data, but it completely falls apart on new stuff. On the other side, you have underfitting, which is like the student who didn't study at all. It's just bad everywhere.
But here's a really subtle trap you can fall into. What if you run your model on the test set? You see the score, and then you go back and tweak your model to get a better score on that specific test set. Well, you've started cheating again. The test set is no longer unseen, and you're not getting an honest picture of how it would do in the real world.
And to stop this from happening, the pros use a three-way split. So you have your training set, that's for learning. Then you have a brand new set, the validation set. That's the data you use to tune all your settings and pick your best model. And only when you're completely done, when you've made your final choice, do you bring out the test set for one last, totally honest grade.
Okay, now that we've set up a way to evaluate our model honestly, we can use our training and validation sets to properly diagnose the two main gremlins that haunt machine learning, bias and variance. You can just think of high bias as underfitting. The model is too simple, it's just not capturing the patterns. So its error is going to be high on the training data and also high on the new validation data. High variance, on the other hand, is our old friend overfitting. The model is too complex, it'll have a super low error on the training data it memorized, but a much, much higher error on the validation data.
And what's so great is you can actually see this. If you plot the error as the model gets more complex, the training error just keeps going down. But look at the validation error. It goes down for a bit, and then it starts to climb back up. That growing gap between the two lines, that is the classic telltale sign of high variance, of overfitting.
Okay, so we've got our diagnostic tools, we know how to spot bias and variance. But now let's talk about a tricky situation where even a fantastic score can be a complete illusion.
So let's say you built an AI to screen for a rare genetic disease. You run it on your carefully prepared test set, and it comes back with 99.9% accuracy. Incredible! That's a huge success, right? Time to publish the paper and celebrate. Well, not so fast. Because what if I told you that this 99.9% accurate model isn't just useless, but it could actually be dangerous?
So here's the catch. It's a problem we call a skewed dataset. If the disease is incredibly rare, think about what a lazy model could do. A model that just predicts no disease for every single person will be right over 99.9% of the time, just by default. It's technically accurate, but it will never, ever find a single person who actually has the disease.
To see through this kind of trick, we need better tools for evaluation. We need metrics that go beyond a simple right or wrong answer and actually tell us about the kinds of mistakes our model is making.
And we start with something called a confusion matrix. It sounds a little intimidating, but it's really just a simple grid that helps us organize our results. It sorts every single prediction into one of four buckets: correct hits, correct rejections, false alarms, and flat-out misses.
Now, from this matrix, we can calculate our first smart metric, precision.
Precision answers a very specific question. Of all the times the model raised a red flag and predicted positive, how many of those times was it actually correct? It's a measure of the quality of our positive predictions.
And our second key metric is recall. This answers a totally different question. Of all the people who were actually positive, what percentage did our model successfully find? This is a measure of completeness. Did we catch all the cases we were supposed to?
And what's so fascinating is that these two ideas are almost always in tension with each other. For something like cancer diagnosis, you need incredibly high recall. You would much rather have a few false alarms, which would be low precision, than miss a single actual case. But for your email spam filter, it's the opposite. You want high precision. You'd rather one spam email sneak into your inbox than have an important job offer get sent to your junk folder.
So, if we often can't have both perfect precision and perfect recall, how do we decide? How do we find that perfect sweet spot for the problem we're trying to solve? Well, we can actually visualize this relationship on something called a precision recall curve. Every single point on this line shows us exactly how much precision we gain or lose as we try to get more or less recall. It lets us look at the trade-off and pick a balance point that we're comfortable with.
And if you need to automatically compare a bunch of different models, we can combine precision and recall into a single number called the F1 score. It's a special kind of average that finds a really nice balance between the two, and it's super useful because it really punishes a model if either one of its precision or recall scores is terrible.
And this really brings us to our final thought. Evaluating an AI isn't just about the math and the graphs, it's about understanding the real-world consequences of its mistakes. For a self-driving car, braking for a shadow on the road is a precision error. It's a false alarm. Annoying, but probably safe. Failing to see a pedestrian crossing the street, that's a recall error, a missed case. So, deciding which error is worse isn't a technical choice. It's a deeply human one.